Okay, welcome to the video on excursion 14.2.A, one-sided limits. We've had an opportunity to look at limits in general and the limit properties, which we will revisit today, but this is kind of an interesting lesson. It's about one-sided limits. The best way to kind of get into it is to actually look at, kind of work backwards. The last example you were asked to do in the guided reading assignment was to consider this function f, whose graph is shown, and to find these 5 one-sided limits. Before we look at these 5 one-sided limits and kind of I reveal the answers to you that you've already kind of considered, I'd like to consider the limit of this function as x approaches 3. So rather than look at a one-sided limit, let's just look at a regular limit. What's the limit of this function as x approaches 3? So that's the first thing you want to think about. We're looking at this graph right in this area right here, because there's x equals 3 right here. And you can see that the function is not really defined at x equals 3. If you come from the left and you get closer and closer to 3 from the left side, then you're getting closer and closer, the function is getting closer and closer to values that are equal to y equals 3. However, if you approach 3 from the right side, so you kind of travel along here, and you're getting closer and closer to an x value of 3 from the right side, you can see that the values of the function are getting closer and closer to, I pause for effect, 5. So because those two values are not the same, we can't say that there's one specific number, one value of y that the function is getting closer and closer to arbitrarily as we get closer and closer to 3. Or what value can we say that we can make this function get as close to as we want to as long as we're within a certain distance of 3 from either side? Well, unfortunately, when you're close to 3 from the left side, from values like 2.9 and 2.99 and 2.999 and even closer, you're getting closer and closer to 3. But when you're getting closer and closer to 3 from the right, like 3.1, 3.01, 3.001, as you're getting just as close as you want to 3 from the right, you're not getting close to 3. You're getting closer and closer to 5. So there is no one value that we can say that you're getting arbitrarily close to. Thus, the limit doesn't exist. But we can consider the one-sided limits. So let's go right down to D and E. I'm really going out of order here, but you can kind of consider this. This notation right here is asking us to find the value of the limit as x approaches 3 from the left-hand side, from values less than 3. Doesn't mean from negative values, it means from values less than 3. Well, here's 3. Again, as we already talked about this, so you're getting closer and closer to 3 from values to the left side of it. Then you're getting closer and closer to a value of 3. E, on the other hand, is asking you for the limit of the same function as you're getting closer and closer to 3 from the right. So now we start looking at this coming this way towards 3, which means we're traveling along these branches of the function. And we've already discussed this, that those values, the value that it gets closer and closer to is 5. So those are the answers to D and E, and I'll show those visually in a moment. But let's go to A. The value of the limit of the function as x approaches 5. Well, you can see that as we get closer and closer to 5 from the left and from the right, we are getting closer and closer to this value, which the function is not equal to there, but that doesn't matter with limits. It doesn't have to be equal to that there, but what happens is this function is equal to, has a value of f of 5 is 2. F of 5 is not 4. However, the limit of the function as x approaches 5 would be 4. That's not a one-sided limit. B is. The limit of the function as x approaches 5 from the left is 4. From the right is 4. And we've already discussed those last two. So here are our answers to those 5 that you would have done at the end of your guided reading assignment for 14.2.3. A couple other additional examples I'd like to look at with you now. Again, this example is kind of comparable to example 1 that's in your text on page 925. You've looked at it. You've looked at that one. Here's another function. The interesting thing here is that since we have a square root, then there are some certain values that x has to be in order for this part of the function to even exist. and x has to be less than or equal to 2. As long as x is less than or equal to 2, then this function is defined. That being said, here is what our graphing calculator would give us for a graph. This is kind of enlarged and zoomed in. And here's our table of values for this function. This function, again, is not defined to the right of this x value right here. Nothing over here. Just when x is less than or equal to 2 is it defined. So it's not even defined at 2. I'm sorry, it is defined at 2. I take that back. It is defined at 2. If you plug 2 in here, you'd get 0, square root of 0 is 0, and you get negative 3. And not surprisingly, that's the answer to our question. The limit of this as x approaches 2 from the left, because we really can't even find this. We can't even find this limit if x approaches 2 in general, because there's no way to kind of look at it from the right. So we can only look at this as a one-sided, in this case, left-handed limit, and that would be equal to negative 3. Now for this particular example 2, which will be the last one we look at, again, we have to use our limit properties. And to remind you of the limit properties, these are the ones, and they're found in your textbook on page 919. They were, we looked at them in our last lesson. Just to remind you again in words, this property says that the limit of a sum of two functions is the sum of the limits. Limit of a difference is the difference of the limits. So what we can basically do is take functions that are really extensive or complicated and look at them and break them up into smaller and smaller parts and take the limit of each part. So when we look at, let me go back to this screen here and bring up the writing tablet so I can do a little writing. Move this over. So when we look at this particular one, we can say that the limit of this function, because it's a square root function, in our fifth property said that when you take the limit of the square root of a function, it's like taking the square root of the limit. So this is equal to the square root of the limit, and I'll just kind of leave some notation out, the limit of the function 16 minus x squared. I guess I'm not going to leave any notation out, as x approaches negative 4 from the right. Again, this function, I should have mentioned before, this function, if you look at a graph of it, is not defined outside of negative 4 to the left and 4 to the right. It's only defined between negative 4 and 4. So when we want to look at the limit as x approaches negative 4 from the right, that's okay because the function is defined between negative 4 and 4. If we want to define this limit as x approaches negative 4 from the left, we'd be in trouble because there's no values to the left. So here's what we have. We have this particular one using our property. So we've used the fifth property. And again, I'd advise you to follow along on page 919. And you can see that property is that because we have a square root. So this is equal to that, which means that the limit of a difference is the difference of the limit. So we're still under the radical sign. So I'm going to rewrite this radical sign. So now we can say that this is equal to the square root of the limit of 16 minus the limit of x squared as x approaches negative 4. Well, the limit of 16, the limit of a constant as x approaches any value is equal to that. So we know that that's equal to 16, so we're still under the radical sign. Again, we're using our limit properties. So we used the limit of a constant property, which is not one of those 5, but tells it that this is 16. And then for here, the limit of x squared would be the limit of x as x approaches 4 times the limit of x. Well, the limit of each of these as x approaches negative 4 from the right is equal to negative 4. So we have 16 minus negative 4 squared, which would be 16 minus 4 squared, which is equal to 0. So we used properties 5 and properties 2 and properties 3. The limit of a constant we used up here. We also used the limit of the identity function, because the limit of the identity function is whatever value we're approaching, which is negative 4. So that's why each of these was equal to negative 4. So we've used a number of properties here. And again, you'd say, well, why can't we just evaluate this? And we can. It's just it's good to review the limit properties, but you can surely have found this if the directions weren't such to use the limit properties. You could have found this by plugging in negative 4, provided that it exists in between negative 4 and 4. And we get 0. So this answer is equal to 0. So one-sided limits, again, we maintain and preserve all the properties of limits as far as computing them. All those properties still hold. That was what mentioned at the top of page 926. The properties are on page 919. I think I had you jot them down when you did that lesson. Now it's time for you to kind of get into this with exercises found on page 927 for 14.2.a, 1 through 24. Remember, you're going to submit the even answers. You can check the odds at your leisure as you're working on them in the back. There is a form online that you can do that, and be sure to hit the submit button. The next thing is this quiz. I didn't write quiz, but this is a quiz on 14.1 through 14.2.a that you'll find online. You'll jot your answers down on a scrap piece of paper, and then you'll have a form to submit that. This is a non-binding grade quiz. It's just to kind of for you to see how you did with these. The answers will be shared in the future, but you can at least get your answers, hold on to them so you can see how you did. And the one assessment that will count, remember, will be the test that we'll have once we get back to the classroom in September. So try these exercises, check your odds as you go, submit your evens, and we're about halfway through this because you got this quiz to do and then a couple of more lessons before we get back to school. If you have any questions, again, don't hesitate to contact me at my email address, and enjoy.